weekend, and we start the week with Monday, the most exciting day of the week, because on Monday we have Inorganic Chemistry class. All right, so just to let you know, I have already added the new homework on our Moodle page. So the homework covers the concepts of acids and bases that we have been covering in the last 2 lectures. And once again, the deadline for you guys to turn in the homework is 2 weeks from today. So you have all the information there in Moodle as well. And of course, I highly recommend you guys to complete the homework. As you remember, the turning in the homeworks and completing the homeworks, this means a significant part of your grade already together with our exam. All right, so today we will start a new topic, oxidation and reduction, which plays a central role in several chemical reactions and also several emerging applications, such as lithium-ion batteries, fuel cells, and also in the production of hydrogen from the water splitting reaction, for example. So oxidation and reduction, we can say that this is on the core of several important applications of inorganic chemistry and several important applications that are central to tackling many of the important challenges that us as humankind are currently facing. All right, so oxidation and reduction is also part of our first section of this course, which deals with the chemistry of the elements. All right. So in our 2 lectures that will cover oxidation and reduction or redox processes, we will cover several topics that can be summarized as: we will study reduction potentials, redox stability, factors governing redox stability, and how to predict redox stability based on the redox properties of a species. We will also learn and understand several approaches that deal with the diagrammatic presentation of potential data, which is very useful to predict reactions and stability as well. And then we will finish by discussing methods for the chemical extraction of the elements from their ores that involve oxidation and reduction reactions. All right, so let's start by giving the main definitions of oxidation and reduction. This is very simple, and probably all you guys know this already, but let's start with this simple concept as we build more and more during the lecture, and then as things get more and more sophisticated. All right, so oxidation refers to the removal of electrons from a species, while reduction implies or means the addition of electrons to that species. And in this lecture, the idea is to develop concepts for understanding why oxidation and reduction reaction occurs. So why and when and how. So we will apply this information for applications in environmental chemistry, chemical analysis, and inorganic synthesis as well. And we will also discuss industrial oxidation and reduction processes, and in particular, processes involved in the extraction of metals from their ores, which constitute a class of important industrial and reduction processes. So regarding the chemical reactions that inorganic compounds undergo, we can safely say that oxidation and reduction reactions, which are reactions in which there is the transfer of electrons from one species to another, these constitute a large class of chemical reactions of inorganic compounds. So oxidation and reduction reactions, in other words, reactions involving the transfer of electrons from one substance to another, is a very important class of molecular transformations in chemistry, and as a consequence in inorganic chemistry as well. So when reduction refers to the electron gain by one species, and electron loss is called oxidation. So oxidation leads to the loss of one electron from the substance, and the reduction means the gain of the electron by the substance. So the joint process involving reduction of one species and oxidation of one species, this reaction involving oxidation and reduction is called a redox reaction, in which the species that supplies electrons, which is the species that oxidizes, because oxidation involves electron loss. So the species that supplies electrons undergo oxidation, it is called the reducing agent or reductant. Similarly, the species that removes electrons or leads to the removal of electron in another substance is the species that reduces, and it's the species that it's called an oxidizing agent or oxidant. And many of these redox reactions, they release a lot of energy, and because of this, they are exploited in combustion and battery technologies, for example. So if we take a look at a lithium-ion battery, which is one of the state-of-the-art in batteries today, present in electronic devices, in cars. So this is constituted by two components or two electrodes. So this is the reaction that occurs in a lithium-ion battery, which involves oxidation and reduction process. So here, this compound is a compound in which lithium ions penetrate between the sheets of carbon atoms in graphite to form an intercalation compound. So here, in this species, lithium is on the metallic state. So the reaction that takes place in the lithium-ion battery, the reaction takes place, this reaction of the incorporation occurs during charging of the battery, and the reverse, so the release of lithium and oxidation takes place during the discharge of the battery. So this is shown here in this diagram. So during the charge, lithium is intercalated into this, in between these sheets in graphite, and then during discharge, it is released, and then it's incorporated into this cobalt oxide. So during discharge, lithium is oxidized to lithium plus, as shown here by this chemical equation here. And then these lithium ions then migrate through the electrolyte to the cathode. And then on the cathode here, they are incorporated into this lithium cobalt oxide. And during this incorporation, so the incorporation of lithium plus ions here in this oxide leads to the reduction of the cobalt from the oxidation number +4 to +3, according to this equation. Therefore, you can see that the way that these batteries work, it's the core of the process of these batteries relies on oxidation and reduction processes. This is how oxidation and reduction is so important nowadays. So oxidation, in which the element or the substance loses electrons, corresponds to an increase in the oxidation number of an element in this substance, and then the reduction corresponds to a decrease in the oxidation number. If we have a reaction in which there is no change in the oxidation number of the elements during the reaction, then we can say that this reaction is not a redox reaction or is not an oxidation and reduction reaction. And one of the main features of compounds having transition metals or D metals is the ability to exhibit multiple oxidation numbers, which is very interesting for various applications, including here in the case of the lithium-ion battery, in which we have cobalt having oxidation states of +4 and +3, for example. And the oxidation state of the element is often reflected on the properties of its compounds and the ability to express the tendency of an element of forming a compound of a particular oxidation state. So these features are very useful. So in a redox reaction, electrons are transferred between species, right? So it's transferred between a species that undergoes oxidation to a species that undergo reduction. So we can use, because of this involves electron transfer, what happens is that we can use some electrochemical methods to build tables of standard potentials in which this transfer of electrons can take place in a redox reaction. So more specifically, the tendency of an electron, for example, to migrate from one species to another in a redox reaction can be expressed in terms of the difference between the standard potentials of the species that are involved in this redox reaction. So I will say this again because this is very important. So if we have two substances involved in a redox reaction, the tendency of the electron to migrate from one species to another can be expressed in terms of the differences between their individual standard potentials. And then we will see examples of this later on to make it easier. And in this case, often the approach that is used in redox reactions, or to understand and to predict and to check if they will happen or not between two species. So one of the approaches states that it is convenient to think of a redox reaction between two different species as the combination of two conceptual half reactions. So we break the overall redox reaction between two species into the combination of two half reactions for each species. So we have that the electron loss, oxidation, and electron gain are displayed explicitly, so they are written down individually, so we can know and clearly see which species is reducing and which species is oxidizing. So we write the redox reaction, we break down the overall redox reaction between individual half reactions for each one of the species involved in these redox processes. So we use half reactions. And the oxidized and reduced species in a half reaction constitute a redox couple. So let's see an example of this to try to make it easier, you know. So here, for example, we have a redox reaction in which zinc in the oxidation state 0 is oxidized to zinc 2 plus, while hydrogen ions are reduced to hydrogen. Here we have oxidation state +1, and here we have oxidation state 0. So this is the complete redox reaction. And what we just said is that it is convenient to write down this complete redox reaction, or to break down this complete redox reaction by writing down specifically the half reactions. So the half reaction for the reduction of hydrogen plus, and the half reaction for the oxidation of zinc, okay? So the complete redox reaction can then be written as a combination of two half reactions, one for reduction and one for oxidation, right? Okay. So here is an example, like demonstrating in this reaction that zinc is undergoing oxidation while hydrogen plus is undergoing reduction, as we just mentioned. And in these types of reactions, what is very nice is that we can use thermodynamic arguments to identify which redox reactions would be spontaneous or to have a natural tendency to occur. And when we talk about thermodynamic arguments, we have that the thermodynamic criterion for a reaction being spontaneous or having a natural tendency to occur is that at constant temperature and pressure, the reaction Gibbs energy change should be negative. So the change in the reaction Gibbs energy should be negative. And the reaction Gibbs energy change is related to the equilibrium constant by this expression, right? So if we need a negative value for the reaction Gibbs energy change, this means that the equilibrium constant for the reaction is positive. So therefore, this is a favorable reaction because if the equilibrium constant is positive or bigger than 1, that means that at equilibrium, the products will dominate the reactants, and therefore the reaction will be favorable. Remember that equilibrium constant involve an expression that involves the concentration or activities of products over reactants. So if it's over 1, that means that the products are favored. So if we talk, like we just mentioned, that it's useful to break down the overall reaction by writing down the half reactions for the species that undergo oxidation or reduction. But here, there is another useful approach in which, in this case, in the redox reactions, we can see that the overall chemical equation can be written as a combination of the two reactions, right? So here we have reduction and oxidation. And then if we combine this expression, or if we sum these two expressions, in this case, reduction and oxidation, we have the overall redox reaction, but it's also useful, or normally in this, when we talk about redox processes, actually the half reactions are not written as one reduction and one oxidation. Normally, a useful approach, and then we will see how useful this is very soon, is that we write the overall equation as, we write the half reactions, both half reaction as reductions. So if we write, in this case, both half reactions as reductions, then the overall chemical equation becomes the difference of the two reduction half reactions. And the same goes for the standard Gibbs energy of the overall reaction. Can be the combination, in case that it's written, in case the half reactions are written as reduction and oxidation, or the differences of the standard Gibbs energies of the two half reactions when they are both written as reduction half reactions. Okay, so here we have these equations, and then by writing the half reactions, we can also see that we can identify the redox couples easily from the half reactions. So in this case is zinc and zinc 2+. So we always write in the direction of reduction in this case, and then here we have H+ and H2. All right, so this is a very important issue here that I already mentioned, that normally it is useful, or it's normal and useful, and this is used in redox reactions. So it's useful to represent all the half reactions as reduction half reactions. So it's useful to represent the oxidation half reaction, which in this case is this one for this example, by the corresponding reduction half reaction. So we write normally both half reactions as reduction half reactions, as shown here. And then the overall redox reaction is the difference between these two reduction half reactions, and the reaction Gibbs energy of the overall process is also the difference between the Gibbs reaction energy of the two reduction half reactions. All right. So in this case, therefore, as I just mentioned, the redox reaction is written, the overall redox reaction in which zinc is oxidized by hydrogen ions is then written as the difference of the two reduction half reactions. All right. So one important thing here is that when we are talking about predicting whether or not a redox reaction is going to take place, whether it's spontaneous or not, and to write the overall redox reaction, actually an important thing is that both half reactions have to be properly balanced. So this is very important. However, the balancing of redox reaction might not be so straightforward. It might be complicated. In this example, it was easy. I showed an easy example first. But for example, if you guys like, let's write the balanced equation for the balanced equation or the balanced redox reaction for the oxidation of iron 2 plus to iron 3 plus by permanganate ions in acid solution. This becomes a little more complicated or require additional attention because some species, like not explicitly mentioned here or not explicitly involved, like in permanganate, for example, permanganate will be reduced to manganese 2 plus. So there are other species in addition to permanganate and manganese 2 plus that are involved in this equation, and then they are not explicitly, and they are not easily identified just by stating like what's the reduction, like what's the equation for oxidation of iron by permanganate ions. So there are other species such as electrons and hydrogen ions that often need to be considered. So actually, there is a systematic approach that needs to be used for the correct balancing of redox reactions. And this approach changes if the medium is acid or if the medium is basic. So I will detail this approach now, and don't be scared. It looks complicated, but it's actually easy. And then we'll work out one example for you guys to see. So how to balance a redox reaction? So first, we write the unbalanced half reactions for the two species as reduction half reactions, as I mentioned before. Then we balance the elements other than hydrogen. So all the elements except hydrogen are balanced. Then we balance oxygen atoms with water in the other side of the arrow. So in acidic solution, we balanced the hydrogen atoms with H+. And if the solution is basic, we balanced hydrogen atoms by adding OH- to one side and water to the other side. Then we balance the charge by adding electrons. And then we multiply each half reaction by a specific factor to make sure that the overall number of electrons match so that we can cancel the electrons in the end. Then we combine the two half reactions by subtracting the one containing the most reducing species from that one containing the most oxidizing species, and then we cancel redundant terms. All right. Sounds complicated, but let's work out an example to show you guys that it's not so difficult. Okay, so the example was to write a balanced equation for the oxidation of iron 2 plus by permanganate ions in acidic solution, right? So we have, let's start with the half reactions. So let's start with the half reaction for the reduction of permanganate ions, which is this half reaction written here. So we start, the first step is to balance all the elements, right, other than hydrogen. So for example, manganese here. So we have one manganese in each side of the equation, so manganese doesn't need to be balanced. Then next step, balance oxygen atoms with water in one side of the row. So here we have 4 oxygen atoms, so we need to add 4 waters to this side. The next step, acidic solution here, right? We are dealing with acid solution. So that means that the next step is to balance hydrogen atoms with H+. So we have 8 hydrogen atoms here, so we probably need to add 8 hydrogen plus to this side, right? And then in the end, we balance the charges with electrons. So here we have -1 plus 8. So we have +7 of charge in this side, and here we have +2. So we need to add 5 electrons here so that we have +2 on the both sides. So this is therefore the half reaction or the half reduction reaction for the reduction of permanganate ions. So you see, it's not so easy just to do by eye. So we need to follow this approach to achieve the correct balancing of the equation. So for iron, of course, it's easier because then if we all follow this approach, or like for iron, it's more intuitive because we just add 1 electron here. So note that in both cases, we wrote this as reduction, have reactions, okay? So the thing is now, so we wrote both have reactions and they are balanced, and then they are written as reduction have reactions. But in the end, we need to be able to cancel the electrons. So electrons in the end cannot appear on the final equation. So we have to multiply the first equation, for example, by a factor of 5. So we have 5 iron 3 plus 5 electrons, giving 5 iron 2 plus. So who is reducing is the permanganate ion. So we can write the overall reaction by taking the half reaction for the reduction of permanganate and subtracting from this equation the reduction of iron 3 plus. Or we can write the permanganate reduction reaction and the iron as the oxidation reaction and just sum 2 equations, and this will give the overall redox reaction, which is given here by this expression. And then in the end, when we do this, we can always double check that it's properly balanced, counting all the atoms and charges on both sides of the equation. All right? Okay, so this is it. So again, here to make this difference, for example, is the same thing as when we do the difference between the reactions, this, this is the same as, so if we are subtracting the permanganate reduction from the iron reduction, this is the same as, so this, this is the same as inverting the iron 2 equation and combining them. So the end result is that we have manganese O4 minus plus 8 hydrogen plus 5 electrons, giving, and then plus 5 iron 2 plus, giving manganese 2 plus 4 others plus 5 electrons plus 5 iron 3 plus, right? And then we can cancel electrons from one side, and then we get this equation that was shown here. All right, was it clear? All right, if that is clear, let's then do an exercise here, writing a balanced equation for the oxidation of zinc metal by permanganate ions in acid solution. So I will give you guys a few minutes to complete this exercise. So remember that we have to write both half reactions as reductions, right? So the half reaction for the zinc oxidation here, writing as a reduction is written here. And then the half reaction for the reduction of permanganate is the one that we just saw in the last example, but I will do it here again. So is permanganate going to manganese 2 plus? So balanced all the elements other than hydrogen. So manganese is balanced oxygen with water. So we have 4 oxygens in this side. So we have to add 4 waters. Then we have to balance the hydrogen with H plus. So we have 8 hydrogens on the right side of the equation. So we need to add 8 hydrogen pluses here. And then to balance the charges, we add 5 electrons. Clear? Okay. So now what we have to do is that we have to combine these two equations in a way that electrons balanced out. So in the overall reaction, we cannot have electrons. So we have to multiply these equations by a factor so that we have we can cancel the electrons in the end. So this can be done by multiplying this first equation by 5 and by multiplying this equation by 2. In this case, we will have 10 electrons in the end. So we have 5 zinc 2 plus 10 electrons, giving 5 zinc 0, and then we have 2 permanganates plus 16H plus 10 electrons, giving 2 manganese 2 plus 8 waters, right? So then if we subtract one equation from another, so if we subtract this equation from this, or this has to be subtracted, is the same as inverting this equation and doing the sum. So in this case, the equation becomes, let me know if you agree with me, 5 zinc 0 plus 2 permanganates plus 16H plus, giving 2 manganese 2 plus 8 waters plus 5 zinc 2 plus. Is that correct? And then here, the electrons cancel each other. All right, so this is the idea. And then in the homework, we will have some examples of balancing of redox reactions that you guys can practice. All right. Okay, so of course the half reactions, they occur in pair, right? Because we are talking about a redox process. So in any actual redox process, the half reactions occur in pair, so they don't occur individually. So we have that they are paired to each other. So if we talk about the Gibbs reaction energy for one half reaction and the Gibbs reaction energy for another half reaction, the Gibbs reaction energy for these processes in an individual manner, they are not significant. What is significant is the differences in the standard Gibbs energies of these two half reactions. So the differences is what has significance. So the differences in the Gibbs reaction energy for the half reactions is what matters. And in order to have a quantitative measure or evaluation of these these differences, we can, for example, set or standardize that one half reaction has Gibbs reaction energy of 0, and then we can use this as a relative measure and then report all other values relative to this half reaction that we stipulate as having 0 of reaction Gibbs, 0 of reaction Gibbs energy. And then by convention, we especially choose the reduction of hydrogen ions at pH 0 and 1 bar of hydrogen as the reaction that possess standard Gibbs energy of 0. And then we can write down all the other reaction Gibbs energies relative to this to this transformation. And actually, we can measure this standard reaction Gibbs energies by setting up a galvanic cell, which is an electrochemical cell or an electrochemical device in which a chemical reaction is used to generate an electric current. And then in this case, the reaction driving the electric current through the external circuit is the reaction of interest. And the potential that can be measured is written as this E here for standard. So the potential that corresponds to the reaction Gibbs energy of a writing reaction, of a half reaction, can be expressed by this equation. So this is how the reaction Gibbs energy relates to the measured potential. And then this E, or this potential, therefore, can be called as the standard potential or standard reduction potential, as it's measured against the reduction of H plus to H2, which is stated as being 0, right? So this is the type of this electrochemical cell or a galvanic cell that can be employed to measure this standard reduction potential for several species. Here, for zinc and zinc 2 plus, so the reduction of zinc 2 plus to zinc, for example, relative to the reduction of hydrogen, right? So this is how the potential, measure potential, relates to the Gibbs energy for the reaction. Okay, so I think we can take a break now. Let's take a 10 minutes break. So it's 1:02. Let's be back at 1:13. All right. So 11 minutes break actually. So no, 10 minutes now. Yeah. So let's be back at 1:13. All right. So I'll see you guys soon. Hello, everybody. So welcome back from our break. And we just mentioned here the concept of this galvanic cell in which we can measure the standard potential or the standard reduction potential for several half reactions relative to the half reaction for hydrogen reduction. And in this case, the difference between the standard reduction potential values in the cell are denoted as the standard reduction potential of the cell. And in this case, a redox reaction will be favorable or spontaneous in the sense that the reaction Gibbs energy is negative and the equilibrium constant is bigger than 1 if the corresponding standard cell potential is positive. Because if the standard cell potential is positive, then the Gibbs reaction energy becomes negative. So for example, for this oxidation of zinc by hydrogen plus, we can see that the standard reduction potential for the cell is positive. Therefore, this reaction is favorable. So zinc, we can say that zinc has a thermodynamic tendency to reduce hydrogen plus ions under standard conditions. In other words, zinc metal will be dissolved in acid because zinc will be converted to zinc 2 plus aqueous. All right. So how, like, from this, we can therefore, by knowing the standard reduction potential for several half reactions or for any half reaction, and these values are obtained from the galvanic cell by measuring the standard reduction potential for the reaction relative to the reduction of hydrogen that corresponds to 0. So with this, we can have the standard reduction potential for several half reactions, and therefore we can kind of use this standard reduction potential for several half reactions, then to calculate the standard potential for several redox reactions, if they will take place or not, for example. So in an example, we can use the standard reduction potential for these half reactions. In this case, the reduction of copper 2 plus to copper and the reduction of zinc 2 plus to zinc, to calculate the standard potential of a copper zinc cell, right? So in this case, the standard potential for the reduction of copper 2 plus to copper is higher than the reduction of zinc 2 plus to zinc, which means that the copper 2 plus is the species who is going to be reduced, and then zinc will be oxidized to zinc 2 plus. So we have that the overall equation here, therefore, is the reduction of copper and the oxidation of zinc. So the standard potential, the standard reduction potential for the cell is the potential for the reduction reaction minus the potential for the oxidation reaction, or minus the potential of the half reduction reaction for the species that will oxidize. So we have to subtract these reduction half reactions. So in this case is 0.34 minus, because we have to subtract from the equation of the reduction half equation that corresponds to the species that will oxidize. So minus 0.76. Therefore, the standard reduction potential for this cell is plus 1.10 volts. Therefore, this is a spontaneous reaction. So one kind of electrochemical device that takes advantage of these oxidation and reduction potentials is a fuel cell. So a fuel cell has emerged also as one of the promising technologies to replace fossil fuels in several sectors, including the transportation and automotive sector as well. So there are some companies working on fuel cells for cars, for example. So in a fuel cell, we convert chemical energy into electric current. So a fuel cell converts a chemical fuel, which can be hydrogen or methanol, for example, into electrical power. So we use hydrogen here as the fuel, for example, in the hydrogen fuel cell, and oxygen from or air, or oxygen from air, as the oxidant. Oxidant, therefore, is the species that is going to be reduced. So in the fuel cell, we have the oxidation of the fuel, hydrogen, oxidized to H+. This generates electrons that goes through the external circuit, and then here they are used to reduce oxygen. And then this is the fundamentals of the work of a fuel cell. So we have in one compartment, in the anode, the fuel is oxidized, and in the other compartment, oxygen is reduced, and then this is leads to the generation of electric current. And this, the fuel cell, therefore, operates as long as fuel is supplied, and it's more efficient and less polluting than combustion devices, for example. All right. So we have seen here that, like, for couples, for half reductions, we have these values of standard reduction potentials, but actually we can understand the origin of this standard reduction potential based on the thermodynamic cycle. So this can be useful to understand the roots, the origins of these standard reduction potentials, and also the origins in the periodic trends, or in the trends of standard potentials for elements across a group or period, for example. So in order to understand these origins or trends in the standard potentials, we have to analyze the thermodynamic factors that contribute to the standard potential of a couple ion M plus to M, for example, here involving a reduction. So in this case, like relative to the reduction of hydrogen. So in this case, we can consider a thermodynamic cycle and the corresponding changes in Gibbs energy that contribute to this overall reaction. So we can see that the atomization and ionization of a metal and the hydration enthalpy of the ions is what contributes predominantly to the value of standard potential. And then we cannot go into much details on this, but this is just for you guys to know how we can kind of systematize and analyze like how these trends in reduction potentials varies for these different elements. So the atomization, ionization, and hydration energies are very important towards dictating the standard reduction potential for a M plus M couple. And here we have some of these data for some of the metals, for example, for you guys to check. All right. And then as we can use this galvanic cell to estimate the standard reduction potential for several half reactions relative to the hydrogen reduction half reaction, we can then construct these tables, for example, of several standard reduction potential for several species, like I show here, right? For fluorine, cerium 4 to cerium 3, and so on. So we can construct these tables of half reactions, always writing the reduction half reactions with the standard reduction potential for several species. And actually, this is the electrochemical series. So the electrochemical series, therefore, can be constructed by assembling or by listing all the reduction, the standard reduction potential for several half reactions of different species, in which we can arrange these half reactions in order of the standard electrode or standard reduction potential, in which we start with the species with the more positive standard reduction potential, in which the species have a high tendency to undergo reduction, so it's a strongly oxidizing agent, to the species with the lowest or strongly negative standard reduction potential, which is a species with a very with a strongly reducing agent. So we can compile these standard reduction potentials in order of the highest, more positive, to the lower, more negative one. And this is the electrochemical series. And this is what is shown in this table, in which the standard reduction potential for the different half reactions are ordered in a way of the higher, more positive, to the lower, more negative values. So this is another representation on how this electrochemical series is constructed. So we start with the most positive values of the standard reduction potential. So these values, these species at the top of the electrochemical series then are the easiest to reduce. So they are strongest oxidizing agent, and therefore the products are the most difficult to oxidize, and they are the weakest reducing agents. And then the species at the bottom are the most difficult to reduce, so they're the weakest oxidizing agent, which indicate that the products here are the easiest to oxidize or the strongest reducing agents. All right, so another important concept in oxidation and reduction reactions is the Nernst equation. And the Nernst equation is very important because we can use the Nernst equation to calculate the cell potential of a reaction at an arbitrary composition of the reaction mixture. In other words, out of equilibrium. And this enables us to judge the tendency of a reaction to go into a particular direction at an arbitrary composition. And in order to know this, we need to know the value and the sign of the reaction Gibbs energy at that composition. So in this case, we have this expression for the reaction Gibbs energy at an arbitrary composition. So here is the equation that we have as an example, in which the constant out of equilibrium here in this case is given by this expression. So this is the expression for Q in this case. And then substituting the standard reduction potential of the cell by this expression, which relates to the Gibbs reaction energy, and this as well, then we get the Nernst equation, which is this equation here, in which the reaction will be spontaneous, even if under the given conditions, the standard reduction potential for the cell will be positive, and this will correspond to a negative reaction Gibbs energy. And at equilibrium, the standard reduction potential of the cell here, this value is 0, and Q is equals to the equilibrium constant. All right, so when we talk about the stability or the thermodynamic stability of a species in solution, we must consider several factors, and these include the solvent, other solutes, the species itself, and also dissolved oxygen. And in order to study or to understand redox stability, we will focus here on types of reactions that can affect the redox stability that result from the which results from the thermodynamic instability of the solute, and we will just briefly discuss some of the kinetic factors. So, for example, one of the important influences on the redox stability is the influence of the pH, because many redox reactions in aqueous solution involve the transfer of H+ as well as electrons. Sorry, I just saw one of the questions here now. Does the odor stay with different temperatures? No. The standard reduction potentials are dependent on the temperature as well. So they all vary. So then for different temperatures, we have to have the data for the standard reduction potential. And then there could be some significant changes in some half reactions that could alter the order. All right, so coming back, so the pH influences the redox stability of several species because many of the reactions involve the transfer of H+ as well as electrons. So the pH will affect the concentration of H+, and therefore it can, the potential and then the stability will depend on the pH. So if we have, for example, a redox couple in which there is a transfer of a specific number of electrons and a specific number of protons in a general equation like this, so oxidized and reduced species, we have that the quotient, the Q value for the reaction is given by this expression, and then like doing some rearrangements here using the Nernst equation, we can arrive that at 25 degrees C, we have this kind of expression that shows that the potential of the cell, in this case, decreases or become more negative as the pH increases and the solution becomes more basic. So this is a way to describe the influence of the pH in a redox reaction in this case. Also, another factor or another phenomenon that can occur that leads to the affects redox stability is reactions of species with water, because water can act as an oxidizing agent when reduced to hydrogen, and also act as a reducing agent when it's oxidized to oxygen, right? So some species can be oxidized by water. So for example, metals with large negative standard potentials, reaction with aqueous acids can lead to the production of H2, unless these metals have a passivated oxide layer on the surface, so a very thin oxide layer on the surface. And the reaction of a metal with water or aqueous acid is in fact the oxidation of the metal by water or hydrogen ions. So what can happen is that the metal can be oxidized by water or acids as well. So this will affect the redox stability of this specific metal. And these reactions or oxidation by water is particularly important or thermodynamically favorable when the metal is a metal of the S block or a 3D metal from group 3 to at least group 8 or 9 and beyond titanium and beyond, or a lanthanoid. So here is an example of such reactions that affect the stability of the species. So when we have like still even like continuing on this loss of redox stability by oxidation by water, so when we have that the standard potential for the reduction of a metal ion to the metal is negative, the metal undergoes oxidation in dilute acids with the evolution of hydrogen. And reactions of manganese and aluminum with moist air are spontaneous, but both metals can be used like for years in the presence of water and oxygen, but actually in this case they survive because they are passivated or protected against this reaction by a thin layer of an oxide, which therefore avoids this oxidation to take place. And when we are talking about like reactions with water or water being oxidation by water, for example, like one of the holy grails in the area of chemistry is the water splitting or using sunlight to break down water or to produce, in order to produce hydrogen from water, in which hydrogen, therefore, can be employed as one of the fuels of the future. So the production of hydrogen from water is one of the future renewable energy solutions. This is one of the holy grails in chemistry, to use like environmentally friendly conditions or just sunlight in the presence of some materials to be able to generate hydrogen and oxygen from water, for example. So this process is named water splitting. So you can see there is a vast literature in this topic. So the oxidation of water, in this case, it's very, this process is in both reactions here, the evolution of hydrogen and the evolution of oxygen that comprises the water splitting have been like extensively studied recently. So in this case, for water splitting, we do both the oxidation and the reduction of water to generate oxygen and the hydrogen. And then when we do this together, this is when the water splitting can be done. And then the interest of this transformation is to be able to use water as an abundant source of hydrogen, right? Which therefore in the end can be employed as a fuel for other applications. So when we talk about reduction by water, only a few oxidizes agents can oxidize water rapidly to give appreciable rates of oxygen evolution. And this is important because for water splitting, both things have to take place together. So we need to have hydrogen evolution or hydrogen production and oxygen evolution or oxygen evolution. So only a few oxidizing agents can oxidize water rapidly enough to give appreciable rates of oxygen evolution. And this is one of the bottlenecks in the field of water splitting. And this barrier for the reaction to take place is a kinetic barrier, because we need to transfer 4 electrons for this reaction to take place to form an oxygen bond from 2 water molecules. And because the rates of these redox reactions are usually controlled by the slow rate at which the oxygen bond can be formed, it remains very challenging to find good catalysts for the oxygen evolution reaction. So this is a very important topic that has been researched recently by several groups in the community, including our own team, that we are very interested in this reaction. So in one of the examples of past works that we have performed is that we employed some bimetallic nanoflowers or bimetallic nanoparticles having this nanoflower-like morphology as catalysts for this oxygen evolution reaction. So what's interesting here in this kind of nanostructure is that this is composed by several islands or branches, very small islands or branches, densely packed together. So we can see here some individual branches. So this is a electron microscopy image of these samples, and you can see here on the scale bar, this corresponds to 5 nanometer. So each one of these islands is around a little bigger. They are around 5 nanometers in this direction and a little bigger in this direction. So the idea here is that this nanostructure is a hybrid material. So these individual branches or islands that comprise this nanoflower structure, they are composed of gold in the interior and a thin layer of iridium oxide on the surface. So why this was done? This was done because the iridium oxide is one of the most active catalysts for this oxygen evolution reaction. So it's a very important material, one of the best performances towards this reaction. But of course, one of the problems of this system is that like it's a little expensive because it's based on iridium, and also like further improvements in performance are always welcome and are always needed. And it's important to make this technology more and more efficient. So the idea here is that we wanted to have a structure of these several islands or branches containing gold covered with a thin layer of iridium at the surface, because gold displays some very interesting optical properties in the visible range. So this enables gold to capture energy from sunlight, and this occurs because of the optical properties of gold, more specifically because of the excitation of the localized surface plasma resonance in gold. So this enables gold to act as an antenna, capturing energy from sunlight, and as iridium is present as a thin layer at the surface, this energy can be transferred to the iridium oxide component and then used to accelerate or improve the rates of oxygen evolution reaction by the iridium oxide. And actually, here in this image, we can see a compositional map also performed in an electron transmission electron microscope in scanning operating mode, in which we can determine the exact locations of gold and iridium in the nanoparticle. And then we can see that gold is represented here by the red color, and the iridium is represented here by the green color. And then we can see this this kind of morphology in which iridium is concentrated at the surface. So by this approach, by using visible light, for example, we were able to go beyond the performance of iridium oxide. So we improved the activity towards the oxygen evolution reaction beyond the benchmark material, which is iridium oxide. So we could make iridium oxide even a better catalyst for the oxygen evolution reaction under visible light, which opens up the possibility of using sunlight in the future. So this is the overreaching goal for the future, to use sunlight as a sustainable energy input and some catalytic materials to enable both the hydrogen evolution reaction and the oxygen evolution reaction, which is particularly challenging as I described in the previous slide. Another factor that contributes to the redox stability is the oxidation of species by atmospheric oxygen. So oxygen from air or dissolved in water can oxidize metals and metal ions in solution. So many elements can occur naturally as the oxidized species, because metals or the metal ions are therefore oxidized by oxygen in air or oxygen dissolved in water. So examples of these oxidized species are soluble oxoanions or ores. And then here we have an example in which iron 2+ can be oxidized by oxygen to iron 3+. All right, and then we see that the potential of this, the standard reduction potential for this process is therefore positive, which makes this process spontaneous. All right, another Another important concept in terms of redox stability is the process of disproportionation and comproportionation. Very difficult words to say in English: disproportionation and comproportionation. All right, so the standard potentials can be used to define the stability and instability of different oxidation states of a species in terms of this disproportionation and comproportionation. So disproportionation refers to a redox reaction in which the oxidation number of an element is simultaneously raised and lowered, as shown here in this chemical equation for copper 1+. In other words, the element undergoing disproportionation serves as its own oxidizing and reducing agent. So here we have this reaction involving the disproportionation of copper plus to copper 2+ and copper 0. And then we can break down here this disproportionation reaction into the two reduction half reactions. And then we can see that by using the standard reduction potential for the two half reactions and calculating the standard reduction potential for this cell or for the overall reaction, we have a positive value, which therefore indicates that the reaction is favorable, or the reaction then becomes spontaneous. All right, so let's now take a look at an example of this. So let's see, can manganese 6 undergo disproportionation into manganese 7 and manganese 2 in acidic aqueous solution through this chemical equation? So here we have the standard reduction potential for the half reactions, and what we can see, we can see that if we subtract the reduction half reaction from the reduction half reaction that corresponds to the oxidation process in the cell, we have that the potential of the cell is 0.76, is positive, which indicates that that yes, this species manganese 6 can undergo disproportionation into manganese 7 and manganese 2. Comproportionation is therefore the reverse of disproportionation. Two species with the same element in different oxidation state can form a product in which the element is in an intermediate oxidation state. So silver 2+ plus silver 0, giving silver plus. So it's the opposite of disproportionation. And the last example regarding redox stability involves the influence of complexation. So complexation in solution can lead, for example, in the case of formation of a complex that is more thermodynamically stable than the individual species in solution, this will favor this will influence the redox stability. For example, the formation of a more thermodynamically stable complex when the metal is in a higher oxidation state of a couple will favor its oxidation. So if we start with the metal and we oxidize this metal to metal 2+, for example, if this metal 2+ forms a thermodynamically stable complex in solution, then this oxidation reaction will be even more favorable. So the complexation will influence the redox stability, in this case, favoring more this oxidation reaction. So this makes the standard potential more negative. Similarly, the formation of a more stable complex when the metal is in a lower oxidation state will favor its reduction, which is the opposite, and then the standard reduction potential becomes more positive. So the ability of a complex here denoted as Ml for metal ligand, formed by the coordination of a ligand to accept or release an electrons, will differ from the corresponding metal aqua ion, or the metal free in solution, not free in a way that is not part of the complex. So here for the metal and here for the complex. And this, it will be different, and then there will be a change in this standard reduction potential for the metal ligand redox couple relative to only the metal. And this change will reflect the degree in which the ligand coordinates more strongly to the oxidized or reduced form of the metal. So if the ligand binds more strongly to the oxidized or reduced form of the metal, this will increase the stability of the oxidized or reduced species, and then this will change the stability or the redox stability of these species. Okay, so next class we will start to discuss some diagrammatic representations of potential data. So we will talk about several diagrams that can be employed to present potential data and what kind of information that they can give us. This is very important and very widespread in textbooks and in the literature in general. There are several useful diagrams that can be used to show the relative stabilities of different oxidation states in aqueous solution for an element. So we have Latimer diagrams that are used for summarizing quantitative data for individual elements. We have Frost diagrams, and then both of these diagrams gives us insights in terms of trends in redox properties, while the Purbake's diagrams display how reduction potentials depend on pH. All right, so we would start the discussion of these diagrams next class, and then I think this is all that I had planned for us today. So anybody has any questions before we finish? If not, thank you very much for being with me today. I will post the notes and video on Moodle now, and have fun with the homework. And if you have any questions at any time, just let me know. And then I will see you guys on Friday. Have a great week, everybody. Bye-bye.